Have you ever paused, perhaps late at night, when the world is quiet and your thoughts feel louder, and asked yourself a question so simple it almost feels dangerous to ask it at all? What was there before everything? Before space stretched out? Before time began its steady march? Before light had anywhere to travel? You see, we are creatures who live inside time. We remember yesterday, we anticipate tomorrow, and we stand, just briefly, in a fragile present. And yet we dare to ask about a moment when even the word before may have had no meaning at all. Well, that is the thing. This question sits right at the edge of science and philosophy, where equations begin to fall silent and language itself starts to fray. Cosmologists talk about the Big Bang not as an explosion in space, but as the expansion of space itself. And when you follow those equations back as far as they will go, you reach a boundary, a place where temperature soars, density becomes infinite, and our best theories simply stop working. Perhaps there was something beyond that boundary, or perhaps the idea of beyond is just a habit of the human mind, looking for causes because that is how our lives unfold. Time, may not be a ticking clock at all. It could be more like a landscape, emerging with the universe itself. Asking what came before the Big Bang might be like asking what lies north of the North Pole. And yet, I suppose the beauty of science is that we keep asking anyway, not to force an answer but to explore possibilities, to open doors rather than close them. This journey is not about certainty. It is about wonder, humility, and the quiet thrill of standing in the presence of the unknown. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. When we hear the words Big Bang, most of us instinctively picture something dramatic and violent. A colossal explosion, perhaps, erupting into an empty void, hurling stars and galaxies outward like shrapnel from a cosmic bomb. It is an image deeply rooted in our intuition, shaped by everyday experience. Fireworks explode, volcanoes erupt, things begin with bangs, and so we imagine the universe doing the same. But well, that picture, as vivid and comforting as it is, turns out to be profoundly misleading. The Big Bang, in the language of modern cosmology, is not an explosion in space at all. And that is the thing that takes a moment to sink in. It is the expansion of space itself. There was no center from which everything flew outward, no surrounding emptiness waiting patiently to be filled. Instead, every region of space was once unimaginably hot, dense, and compact, and then space everywhere began to stretch. Galaxies did not rush through space away from a single point. Space grew between them. You see, it is a subtle distinction, but it changes everything about how we think of beginnings. Imagine, if you will, a simple loaf of raisin bread rising in the oven. As the dough expands, every raisin sees all the others moving away. There is no special raisin at the center of the expansion. Each one could claim, with equal justification, that it is at the heart of things. In much the same way, our galaxy sees others receding in all directions, not because we occupy a privileged position, but because space itself is swelling. This is what the Big Bang describes, a universe that was once compressed into a state of extraordinary density, then began a long, graceful unfolding. And, when we trace this expansion backward using the equations of general relativity, we arrive at a moment when those equations tell us something astonishing. The temperature rises without limit. Density becomes infinite. Distances shrink to nothing. This moment is often spoken of as the beginning, but strictly speaking, it is not a physical description of creation. It is a mathematical boundary, a place where our current theories stop making sense. The Big Bang does not tell us why the universe exists, nor how it was brought into being. It tells us only how it evolved from an early extreme state. This distinction matters, perhaps more than we usually realize. Because when people ask what caused the Big Bang, They are often asking a question that the theory itself was never designed to answer. The Big Bang is not a cause, it is a description, a snapshot of the universe when it was so young that our familiar concepts of space, time, and matter blur together. And that, I suppose, is both humbling and deeply intriguing. Time itself plays a curious role here. In everyday life, time feels absolute. Seconds tick by regardless of what we do. But in physics, time is woven together with space into a single fabric called space-time. And according to our best understanding, this fabric came into being in the Big Bang. If that is true, then asking what happened before the Big Bang may be like asking what lies south of the South Pole. The question assumes a direction that ceases to exist beyond a certain point. You see, in the equations of cosmology, time behaves like a dimension that begins at the Big Bang. There is no earlier moment within the theory, not because we know there was nothing, but because the concept of earlier simply does not apply. This is profoundly counterintuitive. Our minds are trained by biology and experience to think in terms of causes preceding effects. Every story we tell has a beginning, but the universe may not conform to the narrative structures our brains find comfortable. And yet, despite this, we must be careful. The fact that time appears to begin at the Big Bang does not necessarily mean that the universe truly had an absolute beginning. It may instead reflect the limitations of our models. General relativity works exquisitely well across vast ranges of scale, from the motion of planets to the evolution of galaxies. But when pushed to extremes, to the very smallest moments and highest energies, it almost certainly breaks down. At those scales, quantum effects cannot be ignored, and we do not yet possess a complete theory that unites gravity with quantum mechanics. So the Big Bang singularity, that point of infinite density and temperature, may not be a real feature of nature at all. It could be a signpost telling us that our mathematical language has reached the edge of its usefulness. Beyond it, something else may exist, something we do not yet know how to describe. This is where a common misunderstanding creeps in. People often imagine the Big Bang as an explosion that happened at a particular location, at a particular time, within a pre-existing emptiness. But there was no empty stage on which the universe appeared. Space itself was compressed, and time itself was young. The universe did not expand into something. It expanded, full stop. And perhaps, before that expansion, the notions of into and before simply do not apply. Well, let us pause for a moment and reflect on how extraordinary that is. We are creatures who evolved on a small planet orbiting an ordinary star in a vast and ancient cosmos. Our intuitions are shaped by survival, not by the demands of fundamental physics. And yet, through careful observation and quiet reasoning, we have arrived at a picture of the universe that challenges the very grammar of our thoughts. The Big Bang Theory emerged not from philosophical speculation, but from evidence. Galaxies are moving away from us, their light stretched to redder wavelengths by the expansion of space. The universe is filled with a faint glow, the cosmic microwave background, the cooled remnant of an era when the cosmos was hot and opaque. The abundances of light elements match the predictions of a universe that was once dense and fiery. All of these facts point to an early phase of rapid expansion, but none of them require that this phase be the ultimate beginning of everything. And that is the quiet but profound point at the heart of this chapter. The Big Bang is not the origin story of existence itself. It is the earliest chapter we can currently read with confidence. Before that, the pages are missing, or perhaps written in a language we have not yet learned to speak. When we say that time has meaning only after the Big Bang, we are really saying something subtle about our descriptions of reality. Physical time is defined by change, by processes unfolding according to laws. If the laws themselves are changing, or if space-time itself is emerging, then the familiar notion of time may dissolve. There could be a deeper structure from which time arises, just as temperature arises from the collective motion of particles. No single molecule has a temperature, and yet temperature is real. Perhaps time is like that, not fundamental, but emergent. This idea opens the door to remarkable possibilities. If time emerged with the Big Bang, then the universe may not have begun in the way stories usually begin. There may have been no moment of creation, no first tick of a cosmic clock. Instead, the universe could be a self-contained structure, complete in itself, with no external cause. Or it could be part of a larger reality, in which what we call the Big Bang is merely a transition, a phase change like water freezing into ice. I suppose what makes this so compelling is not just the science, but the way it forces us to confront the limits of human understanding. We want beginnings because beginnings give us a sense of order. They allow us to draw lines and tell stories. But the universe is under no obligation to satisfy that desire. It may be stranger, quieter, and more subtle than we imagine. And yet, we should not mistake this strangeness for defeat. On the contrary, it is an invitation. The recognition that the Big Bang does not explain everything is not a failure of science. It is a sign of its honesty. Science does not pretend to know what it does not know. It maps the territory it can reach and marks the edges with questions. As we stand at that edge, looking back toward the earliest moments we can describe, we begin to sense something even more unsettling. If time itself is part of the universe, then the idea of a before may be meaningless. And if before is meaningless, then many of our deepest questions may need to be rephrased or perhaps gently set aside, which leads us almost inevitably to a deeper puzzle. If there was no before in the usual sense, what does that say about time itself? Is time a fundamental ingredient of reality, or is it something that arises only under certain conditions? And if it can arise, can it also disappear? These questions pull us forward, beyond the comforting language of beginnings, toward a place where time loosens its grip and intuition must learn to let go, and that is precisely where our journey naturally drifts next. And so, as we drift naturally from that edge where our equations fall quiet, we arrive at an even more unsettling realization. If the Big Bang is not simply an event within time, but the moment at which time itself becomes meaningful, then the familiar idea of before begins to dissolve. You see, we tend to treat time as a universal backdrop, something that flows steadily no matter what the universe is doing. But modern physics asks us to abandon that comfort. Time, it turns out, is not an absolute stage on which reality performs. It is a physical dimension, woven into the structure of the universe itself. In everyday life, time feels so fundamental that questioning it seems almost absurd. We wake, we sleep, we grow older. Cause follows effect with reassuring regularity. But physics tells a more subtle story. In Einstein's theory of relativity, time is inseparable from space. They form a single entity, space-time, flexible and dynamic. Mass and energy tell space-time how to curve, and curved space-time tells matter how to move. Time slows near massive objects. Clocks tick differently for observers moving at different speeds. There is no single, universal now shared by the entire cosmos. And that, I suppose, is already strange enough. But when we apply this framework to the universe as a whole, something remarkable happens. As we trace the cosmic expansion backward, not only does space shrink, but the time dimension itself seems to contract toward a boundary. According to general relativity, this boundary is the Big Bang. And crucially, time does not extend beyond it. There is no earlier moment within the theory. Not because we have proven there was nothing, but because the mathematical structure simply does not allow us to define a time coordinate beyond that point. This is why physicists often say that asking what happened before the Big Bang is like asking what lies north of the North Pole. The question assumes a direction that ceases to exist. At the North Pole, every direction south makes sense, but north does not. It is not hidden. It is not forbidden. It is simply undefined. In much the same way, if time begins at the Big Bang, then before is not a location we have failed to reach. It is a concept that may have no meaning in that context. And this is where human intuition struggles. Our brains are storytelling machines. We evolved to navigate a world where events unfold in sequence. We look for causes, origins, and explanations that fit into a linear narrative. Fire comes from sparks. Rivers begin at springs. Lives start with birth. So when we encounter a model of the universe that refuses to offer a first moment in the usual sense, it feels deeply unsatisfying, almost like a trick. But perhaps the discomfort is telling us something important. Perhaps it is not the universe that is incomplete, but our expectations. Time, after all, may not be fundamental. It could be emergent, arising only when the universe reaches a certain level of complexity. Just as temperature emerges from the collective behavior of countless particles, time might emerge from the relationships between events. No single event carries time within it. Time is something we infer from change. In relativity, space-time is not something added to the universe. It is part of what the universe is. Remove space-time, and there is no arena for events to occur. So if space-time itself is born in the Big Bang, then speaking of earlier events becomes problematic. There is no coordinate system in which to place them, no clock that could have been ticking, no sequence to arrange them into. And yet, this does not mean that reality itself sprang from literal nothingness in a philosophical sense. That is a common leap, but an unjustified one. Physics is careful here. When it says time begins, it is making a statement about the limits of a model, not necessarily about the absolute nature of existence. The equations tell us that time, as we understand and measure it, becomes meaningful only after the Big Bang. What lies beyond that boundary, if anything, may require a different conceptual framework entirely. This is why the question of before the Big Bang is so powerful. It exposes the limits of language. Words like before, after, cause, and beginning are tools shaped by life inside time. When we try to use them outside their domain of applicability, they begin to wobble. The question is not foolish, it is profound. But it may be poorly formed, like asking what color a sound is. You see, even in our everyday experience, time behaves in ways that hint at its strangeness. Psychological time stretches and contracts. Moments of fear feel long. Years can vanish in memory. The present itself is elusive. By the time you notice it, it is already gone. Physics adds another layer, showing us that simultaneity is relative, that different observers slice space-time into past, present, and future in different ways. So when we try to imagine a universe without time, we are not just confronting an abstract idea. We are confronting the scaffolding of our own consciousness. Our sense of self is deeply tied to memory and anticipation. Remove time, and identity itself begins to blur. Perhaps that is why the idea that there is no before feels so unsettling. It threatens not only our cosmology, but our sense of meaning. We want the universe to have an origin story, because stories are how we make sense of existence. But the universe may not share our narrative instincts. And yet, even within relativity, time is not entirely banished from the discussion. It is transformed. Time becomes one dimension among others, measurable, flexible, influenced by matter and energy. In this view, the universe is not something that happens. It simply is, as a four-dimensional structure. Past, present, and future coexist within space-time. What we experience as the flow of time may be a feature of consciousness moving through that structure. If that is the case, then the Big Bang is not the moment when the universe began to exist, but the boundary of our temporal perspective. It is the edge of the space-time map we can draw. Beyond it, the map runs out, not necessarily the territory. And that brings us back to the core fact of this chapter. When there is no time, there is no before. The question dissolves, not because it is forbidden, but because it relies on a category that no longer applies. This is deeply counterintuitive, but physics has taught us again and again that intuition, shaped by a narrow slice of reality, is not a reliable guide to the cosmos. Still, it is worth lingering with the discomfort, because within it lies a clue. If time is a physical dimension, and if it can have a beginning, then perhaps it can also have a different form. Perhaps the universe is not required to have a single temporal structure extending infinitely in both directions. Perhaps there are models in which time stretches endlessly into the past, or cycles, or even branches. And indeed, once physicists began to seriously consider the idea that time might not be fundamental, new possibilities emerged. Models in which the universe does not have an absolute beginning. Scenarios where the Big Bang is not the birth of everything, but a transition from a previous state. In these ideas, time may exist in some form beyond the Big Bang, even if our familiar version of it does not. So while relativity teaches us that before may be meaningless within a certain framework, it also invites us to explore what happens when that framework is extended or replaced. What if the universe has always existed in some form? What if time stretches infinitely backward, even if it passes through phases radically different from our own? As we begin to entertain these possibilities, we find ourselves gently stepping beyond the idea of a universe with a single origin. We start to glimpse models where existence has no first moment, where the cosmos may be eternal, reshaping itself endlessly. And that thought, quiet and radical, carries us naturally onward, toward the idea that perhaps the universe did not begin at all, but has always been, changing its form across an infinite depth of time. And so, standing at that threshold where time itself begins to feel optional rather than mandatory, the mind starts to wander in a new direction. If the idea of a first moment is not as solid as we once believed, then perhaps the universe does not require a beginning at all. Perhaps existence does not start with a bang, but simply is, always changing, always unfolding, but never truly starting or stopping. This is where the notion of an eternal universe quietly enters the conversation. It does not arrive with drama. It slips in almost politely, as if to say, well, what if the question of origin is the wrong question altogether? What if the universe has no first page? What if time, in some form, stretches endlessly into the past, just as it may stretch endlessly into the future? You see, for much of human history, the universe was assumed to be eternal by default. Ancient thinkers looked at the heavens and saw patterns that repeated night after night, season after season. The stars seemed fixed, unchanging, beyond the reach of decay. It felt natural to imagine a cosmos without birth or death. The idea that the universe had a beginning is, in fact, a relatively modern one, born from the discovery that space itself is expanding. But expansion does not automatically demand a beginning. That is the subtlety. If you see footprints leading away from you, it is tempting to assume there must be a first footprint somewhere behind. But perhaps the ground itself is moving. Perhaps the pattern does not trace back to a single starting point, but to a process without origin. In some cosmological models, the universe exists eternally, though not in a static form. It may expand and contract. It may pass through different phases, governed by different physical laws. What we call the Big Bang could be merely one transition in an endless sequence, not the creation of everything, but a reshaping of what already existed. One such idea imagines a universe that undergoes cycles. Expansion gives way to contraction. The cosmos grows, cools, and thins. Then gravity slowly gathers everything back together. Eventually, the universe becomes dense and hot once more, not unlike the conditions we associate with the Big Bang. Then, instead of collapsing into nothingness, it rebounds. A new expansion begins. A new cosmic era unfolds. In this picture, time does not have a beginning. It extends infinitely into the past, marked not by a single origin, but by an endless rhythm. Each Big Bang is not the start of everything, but the start of something. A new chapter, not the book itself. And there is something deeply appealing about this. It resonates with patterns we see all around us. Day follows night, seasons turn, stars are born, live and die, only for their remnants to seed new generations. Why should the universe itself be exempt from such cycles? Yet, of course, physics demands more than poetic symmetry. The question is not whether an eternal universe feels satisfying, but whether it is consistent with what we observe. And this is where things become subtle, and perhaps even more interesting. One of the challenges facing eternal models comes from entropy. Entropy is often described as a measure of disorder, though that is a simplification. More precisely, it is a measure of how many ways a system can be arranged internally without changing its overall appearance. The second law of thermodynamics tells us that entropy tends to increase. Systems evolve from ordered states to more probable, more disordered ones. If the universe has existed forever, one might expect entropy to have reached a maximum long ago, a kind of cosmic heat death where no meaningful change is possible. And yet, here we are, in a universe full of structure, gradients, stars blazing with energy, galaxies swirling with motion. How can that be if time stretches infinitely into the past? Some eternal models address this by proposing that entropy behaves differently on cosmic scales. Perhaps entropy resets or redistributes during contraction phases. Perhaps the arrow of time itself reverses in certain regimes. Or perhaps our observable universe is only a small region within a much larger eternal structure, one where low entropy conditions can arise naturally, even if the overall system is timeless or cyclic. Another approach imagines that the universe is always expanding, but that expansion has no beginning. In this view, the Big Bang is not the start of expansion, but a moment when expansion changed character. The universe may have been expanding forever, but at some point transitioned into the hot, dense phase we can observe evidence for today. This is a difficult idea to visualize because we are used to thinking of expansion as something that must start. But mathematically, it is possible to construct models where space-time extends infinitely into the past, always expanding, yet still producing a phase that looks very much like a Big Bang from our perspective. In such models, time does not end at a singularity. There is no mathematical cliff where the equations blow up. Instead, the universe has a long, perhaps infinite, prehistory that is largely inaccessible to observation. Signals from that era may be diluted beyond recognition by expansion. Information may be lost or scrambled. The universe remembers its past imperfectly, and that raises an important point. Even if the universe is eternal, that does not mean we can know it. Our observational reach is limited. Light travels at a finite speed. The universe has a finite age since the Big Bang phase we observe. There is a horizon beyond which we cannot see. Eternal time does not guarantee eternal knowledge. This limitation is not a weakness of science. It is a feature of reality. We are embedded within the universe we study. We cannot step outside it. We cannot rewind it. We can only observe the traces that have survived the long journey to our telescopes. And yet, within those traces, physicists search for hints. Subtle patterns in the cosmic microwave background, unexpected correlations in large-scale structure, deviations from the simplest models of expansion. These could, in principle, carry whispers from a time before what we call the beginning. There is also a philosophical shift that comes with eternal models. If the universe has no beginning, then it does not require a cause in the traditional sense. It simply exists, not because it was made, but because non-existence was never an option. This can feel unsatisfying, even unsettling. We are deeply attached to explanations that trace things back to an origin, but perhaps that attachment is a reflection of our own finite nature. We are born, we live, we die. Everything we know has a start. Why should the universe be any different? Well, maybe because the universe is not a thing within time. It is the context in which time itself unfolds. In an eternal universe, the question shifts. Instead of asking why there is something rather than nothing, we might ask why reality has the structure it does. Why these laws? Why this pattern of change? The mystery does not disappear. It simply moves. And there is something quietly profound in that. The absence of a beginning does not strip the universe of meaning. If anything, it deepens the mystery. An eternal cosmos is not simpler than a created one. It is stranger, more subtle, less accommodating to human narratives. Of course, eternal models are not without their problems. Some versions run into mathematical inconsistencies. Others conflict with observations. And some may be unfalsifiable, drifting toward philosophy rather than physics. This is why cosmology remains a living, breathing field, full of debate and revision. But what is undeniable is that the idea of an eternal universe is not fringe speculation. It arises naturally when we push our theories to their limits, when we refuse to stop asking questions just because the answers become uncomfortable. And perhaps that is the deeper lesson here. The Big Bang may not be the beginning of everything. It may be the beginning of our story, the part we can tell with evidence and equations. Beyond that, there may be a vast, uncharted expanse of time, stretching backward without limit, filled with forms of existence we have yet to imagine. As we sit with that thought, another possibility begins to shimmer into view. If the universe can exist eternally, changing its shape and behavior across time, then perhaps it does not merely persist. Perhaps it repeats. Perhaps existence itself has a rhythm, a cosmic pulse, expanding and contracting, dying and being reborn in an endless dance. And that gentle idea, almost musical in its symmetry, carries us naturally toward the next chapter of our exploration, where the universe does not just endure, but oscillates. And so the idea that the universe might endure forever, changing yet never truly beginning, gently deepens into something even more rhythmic. If existence can persist without origin, perhaps it does not merely stretch endlessly like a straight line, but bends back on itself, repeating, echoing, breathing. This is where the notion of a cyclic universe emerges, not as a radical break from what we have discussed, but as a natural continuation of it. You see, once we allow ourselves to imagine that the Big Bang was not the absolute beginning, it becomes possible to reinterpret it entirely. Instead of a birth, it becomes a rebirth. Instead of creation, a transformation. In a cyclic universe, the Big Bang is just one beat in an infinite cosmic rhythm. Expansion is followed by contraction, cooling gives way to heating, structure dissolves, only to be reassembled in a new form. The universe in this picture is not a one-time event. It is a process, a vast oscillation playing out across scales of time so immense that words like long and short lose their meaning. Each cycle may last trillions upon trillions of years. Galaxies form, stars ignite, life may even emerge, and then, slowly, gravity begins to assert itself on the grandest scale. As expansion continues, it eventually reaches a point where the outward motion slows. Galaxies drift farther apart, stars burn out, black holes dominate the landscape, and then, in some versions of the theory, the expansion halts altogether. Gravity takes over. The universe begins to contract. This contraction phase is sometimes called the Big Crunch. Space itself shrinks. Distances collapse. Temperatures rise. Matter grows denser and denser. The universe, once vast and cold, becomes small and hot again. And here, something extraordinary may happen. In classical physics, such a contraction would end in a singularity, much like the one we associate with the Big Bang, an endpoint where density becomes infinite and the laws of physics collapse. But quantum gravity, though still incomplete, hints at another possibility. Instead of collapsing into nothingness, the universe may rebound. This rebound is known as the Big Bounce. At the moment when contraction reaches an extreme, quantum effects generate a kind of pressure that resists further collapse. Space stops shrinking and begins to expand once more. A new cycle begins, a new Big Bang, not born from nothing, but from the compressed remains of the universe before. And, there is something profoundly elegant about this idea. The universe does not need an external cause. It carries its own history forward, cycle after cycle, reshaping itself endlessly. Creation is replaced by continuity. Beginning gives way to recurrence. In such a universe, what we call the Big Bang is not the start of everything. It is simply the transition between phases. The universe before ours may have been vast, old, and filled with structure of its own. Galaxies and stars from that previous era may have long since been destroyed, their matter compressed and transformed, but not erased. Energy, after all, is conserved. Matter can change form, but it does not vanish without trace. In a cyclic universe, the ingredients of our cosmos may be recycled remnants of a much older one. The atoms in your body could have passed through countless cosmic lives, forged in stars that shone in universes long before ours. This idea resonates deeply with the human sense of continuity. We see cycles everywhere: birth and death, growth and decay. In nature, nothing truly disappears, it transforms. Perhaps the universe itself follows the same principle. Yet, as always, the details matter. A major challenge for cyclic models lies again with entropy. Each cycle, according to the second law of thermodynamics, should increase entropy. Disorder should accumulate. If that is the case, then each new cycle would be more disordered than the last, until meaningful structure becomes impossible. To address this, some cyclic models propose mechanisms by which entropy is diluted or reset between cycles. For example, during long periods of expansion, entropy may become so spread out that each new contraction effectively starts fresh. Others suggest that the universe sheds entropy into dimensions or regions we cannot observe. These ideas are speculative, but not arbitrary. They emerge from attempts to reconcile cosmology with fundamental physics. In particular, approaches to quantum gravity suggest that space-time at the smallest scales behaves very differently from our everyday intuition. Singularities may be avoided. Continuity may replace abrupt endings. Another intriguing aspect of cyclic universes is the possibility that information could pass from one cycle to the next, not in the form of intact galaxies or recognizable structures, but as subtle imprints, tiny irregularities, slight anisotropies, patterns encoded in the fabric of space-time itself. This raises a tantalizing question. Could we, in principle, detect evidence of a previous universe? Could the cosmic microwave background, that faint afterglow of the early universe, carry scars from a time before our Big Bang? Some researchers have searched for unusual patterns, circular features, or anomalies that might hint at collisions or structures from an earlier cycle. So far, nothing definitive has been found. The data is subtle. Noise competes with signal. Interpretation is fraught with uncertainty. And yet, the possibility remains. The universe may remember more than we think, even if that memory is faint and fragmented. There is also a philosophical shift that comes with cyclic thinking. In a cyclic universe, there is no ultimate beginning and no final end. Time may be infinite, but not linear. It loops, stretches, and renews itself. The arrow of time, usually tied to entropy increase, may behave differently across cycles. In some models, time continues smoothly through each bounce. In others, the direction of time reverses during contraction. What we perceive as the forward flow of time may be local, not global, a feature of our particular phase of the cycle. This challenges deeply held assumptions. We tend to think of the past as fixed and the future as open. But in a cyclic universe, the distinction may blur. The future of one cycle is the past of another. History becomes layered, recursive, less like a straight story and more like a melody repeating with variations. And yet, despite its beauty, the cyclic universe is not something we can accept simply because it feels right. It must confront observation. It must match the precise measurements of cosmic expansion, background radiation, and large-scale structure. Some versions do, others fail. The field is alive with debate. What is remarkable is not whether any particular model is correct, but that such models are taken seriously at all. They represent a willingness to let go of the idea that the universe must have a single moment of origin. They reflect a growing recognition that our deepest questions may require us to think in ways that feel almost unnatural. As we imagine a universe endlessly reborn, another thought quietly emerges. If the cosmos can cycle through expansions and contractions, if Big Bangs can occur again and again, then perhaps our universe is not unique. Perhaps these cycles are just one way among many that reality expresses itself. And that thought, subtle at first, begins to pull us toward an even stranger possibility, a universe not born from a previous one, but emerging spontaneously from something that looks, at first glance, like nothing at all. A vacuum that is not empty, but alive, with possibility. And so, from cycles and rebirth, our journey drifts onward toward the quantum void itself. And so, from the grand breathing of a cyclic cosmos, where entire universes may rise and fall like slow tides, our attention drifts inward, deeper, toward something that at first sounds almost paradoxical. If the universe can be reborn from the ashes of a previous one, then perhaps it does not even require ashes at all. Perhaps it can arise from what we would casually call nothing. And here, well, this is where language begins to mislead us most of all. Because in modern physics, nothing is not nothing. You see, when physicists speak of a vacuum, they do not mean an absolute void, a complete absence of everything. They mean the lowest energy state of a field. A quantum vacuum is not empty space. It is a restless, seething arena of potential. Fields permeate all of space, even where no particles exist. And these fields are never perfectly still. They fluctuate, they tremble, they borrow energy briefly, then return it, as allowed by the uncertainty principle. This is one of the most counterintuitive discoveries of quantum physics. The vacuum is alive. Even in the deepest emptiness imaginable, pairs of particles and antiparticles can momentarily flicker into existence, then annihilate one another, leaving no trace except subtle measurable effects. These are often called virtual particles, though that name can be misleading. They are not imaginary. Their consequences are real. The vacuum has energy. This vacuum energy can exert pressure. It can influence how particles move, how forces behave, even how space itself expands. And once you accept that, a remarkable idea begins to take shape. If the vacuum is not truly empty, then perhaps the universe itself could emerge from it, not as an explosion, not as a deliberate act, but as a natural fluctuation. In quantum mechanics, events do not always require causes in the classical sense. Processes can occur spontaneously, provided they obey the underlying laws and conservation rules. On very small scales, particles can appear and disappear without violating physics, as long as they do so quickly enough. Energy conservation becomes a statistical rule, not an absolute prohibition. Now, take that idea and stretch it to its most extreme limit. Imagine a quantum fluctuation not of a particle, but of space-time itself. A tiny region where the vacuum momentarily rearranges, producing a pocket of expanding space. If the conditions are right, that expansion could feed on the vacuum energy, growing, rather than collapsing back into nothing. And that is the astonishing suggestion behind some models of cosmology. The universe may have begun as a quantum fluctuation of the vacuum, not created from nothing, but from a state with no particles, no radiation, no classical spacetime, yet still governed by quantum laws. In this picture, the Big Bang is not a singular act of creation. It is the amplification of a tiny random event, a fluctuation that did not fade away, but instead inflated, becoming the vast cosmos we inhabit. This idea challenges our instincts about causality. We want to ask what caused the fluctuation. But in quantum theory, some events are simply allowed. They do not need a trigger. They happen because they can. And perhaps that is deeply unsettling. It suggests that existence itself may not require a reason in the way we usually understand reasons. The universe may exist because the laws of physics permit it to exist. No more, no less. The notion of a universe from the quantum vacuum also reshapes how we think about nothingness. Philosophically, nothingness is often imagined as the absence of all properties, all structure, all potential. But the quantum vacuum is not that. It is a structured state. It has rules. It has fields. It has energy. It has possibilities. So when we say the universe came from nothing, what we really mean is that it came from a state with no classical objects, no stars, no space as we know it, no time ticking away. But still, there was something, a framework of physical law. And this raises an even deeper question. Where did those laws come from? Well, perhaps that question, too, is shaped by our habits of thought. Laws in physics are not commands imposed from outside. They are descriptions of regularities. They summarize how reality behaves. It may be meaningless to ask why those laws exist, just as it may be meaningless to ask why logic is logical. Still, the idea that the universe could arise from a quantum vacuum has profound implications. It suggests that creation is not a rare or miraculous event. It may be commonplace. Given enough time, universes may pop into existence wherever the conditions allow. In such a view, our universe is not special because it exists. It is special because it persists. Many fluctuations may occur and vanish almost immediately. Only those that expand rapidly enough avoid collapse. Survival becomes the key. This naturally leads us toward the concept of inflation, though we will linger there later. For now, it is enough to note that a rapidly expanding space-time can stabilize a nascent universe, preventing it from annihilating itself back into the vacuum. Expansion dilutes energy densities. It smooths irregularities. It turns a fragile fluctuation into a self-sustaining cosmos. There is also a subtle but important point about energy conservation here. If the universe has positive energy in the form of matter and radiation, where does that energy come from? The answer may be that it is balanced by negative energy associated with gravity. Gravitational fields carry negative potential energy. As the universe expands, the total energy may remain exactly zero. A universe with zero net energy can, in principle, arise without violating conservation laws. It is like a loan that balances perfectly. Matter and gravity cancel each other out. Something from nothing, without breaking the rules. This idea has a strange elegance to it. The universe as a zero-sum game. Existence as a delicate balance rather than an excess. And yet, elegance does not guarantee truth. These ideas are speculative. They rely on extrapolating quantum mechanics into regimes we cannot yet test directly. We do not have a complete theory of quantum gravity. We do not fully understand how space-time behaves at the smallest scales. But what we do know is that the vacuum is not empty. Its effects are measurable. They influence particle physics, cosmology, and the evolution of the universe. Dark energy, for example, may be related to vacuum energy, though the details remain deeply mysterious. This brings us to another remarkable possibility. If the vacuum has energy, then it can drive expansion. In fact, it can drive accelerated expansion. A universe dominated by vacuum energy expands faster and faster. And if such a phase occurred in the very early universe, it could explain why the cosmos appears so uniform and flat on large scales. In this light, the Big Bang begins to look less like a singular moment and more like a transition. A shift from a quantum-dominated vacuum state to a hot, particle-filled universe. A phase change, not unlike water freezing or boiling, but at a scale beyond ordinary comprehension. And perhaps that is the key insight. The universe may not have been created. It may have condensed, precipitated out of a deeper quantum reality. This idea also softens the sharp boundary between something and nothing. Instead of a stark divide, there is a gradient, a continuum of states, from highly structured to minimally structured. The quantum vacuum sits near one end of that spectrum. Our universe occupies another. From this perspective, the question of what was before the Big Bang becomes almost irrelevant. There may have been no before in time, but there may have been a more fundamental state, timeless or differently timed, from which our universe emerged. And notice how this echoes themes we have encountered before. The emergence of time, the idea that beginnings may be transitions rather than origins, the sense that our familiar categories fail us at the deepest levels. The quantum vacuum universe does not eliminate mystery. It relocates it. Instead of asking what came before everything, we ask what underlies everything. Instead of seeking a first cause, we seek a deeper description. And as we sit with that, another thought naturally arises. If universes can emerge from the vacuum, if this process is allowed by the laws of physics, then perhaps it does not happen just once, Perhaps it happens repeatedly. Perhaps many universes exist, each born from fluctuations in a vast, inflating background. The vacuum, after all, may not be static. It may itself be dynamic, expanding, spawning regions that become universes in their own right. And that idea, quiet but radical, draws us onward, toward a picture in which our universe is not alone, but one bubble in a much larger cosmic foam, forever growing, forever giving birth to new realms. And so, from the quiet idea that universes might simply arise from the restless energy of the quantum vacuum, our imagination is carried outward again toward a picture even larger, even more unsettling in its scale. Because if a single universe can emerge from a fluctuation, then perhaps that process does not happen just once. Perhaps the background itself is not calm, not static, but endlessly active. Perhaps space is always expanding somewhere, giving birth to regions like ours again and again. And this is where the idea of eternal inflation begins to take hold. You see, inflation was originally proposed to explain some curious features of our universe. Why does space look so smooth and uniform on the largest scales? Why does the geometry of the cosmos appear almost perfectly flat? Why are distant regions, seemingly too far apart to have ever communicated, so remarkably similar? Inflation offers an elegant answer. In the earliest moments of our universe, space expanded extraordinarily fast, faster than anything we see today. In a tiny fraction of a second, a microscopic region was stretched to cosmic proportions. But when physicists examined the mathematics more carefully, they noticed something intriguing. In many models, inflation does not end everywhere at once. It stops locally, in patches. In one region, inflation ends, energy is released, particles form, and a hot Big Bang-like phase begins. That region becomes a universe like ours. But elsewhere, inflation continues. And that is the crucial point. Inflation may be eternal. In this picture, there exists a vast background of space that is still inflating, still expanding at an incredible rate. Within this inflating sea, small pockets occasionally form where inflation ends. Each pocket becomes a bubble universe. Our universe may be one such bubble. Its Big Bang was not the beginning of everything, but the moment inflation ended locally for us. Before our Big Bang, then, there was something. Not a previous universe like ours, not stars or galaxies, but an inflating space-time. A region governed by a different state of energy, expanding relentlessly, indifferent to the passage of ordinary time as we experience it. This changes the meaning of before in a subtle but important way. There may not have been a before within our universe, because time as we know it began with our Big Bang. But there could have been a before in a broader sense, in the inflating background. Time may exist globally, even if it has a beginning locally. It is a bit like living inside a bubble rising in boiling water. From inside the bubble, the moment it forms feels like a beginning. But the water around it has been there all along, bubbling continuously. In eternal inflation, space itself is the medium that persists. Universes are events within it. And perhaps what is most astonishing is that this process never ends. As long as inflation continues somewhere, new universes will keep forming. The cosmos becomes a kind of cosmic factory, endlessly producing distinct regions, each with its own history, its own Big Bang, its own arrow of time. Our universe in this view is not unique. It is typical. This idea forces us to confront the scale of reality in a new way. We are accustomed to thinking of the universe as everything that exists, but eternal inflation suggests that what we call the universe is merely our observable region, a small bubble in a much larger structure. Beyond our cosmic horizon, there may be countless other bubbles, forever out of reach. And here, intuition once again falters. Space between bubbles may be expanding so fast that no signal can ever pass from one to another. They are causally disconnected, separate realities, not in a mystical sense, but in a precise physical one. The inflating background itself is strange. It is not empty, but filled with a high-energy vacuum state. This vacuum drives expansion. It has a pressure that causes space to stretch exponentially. And because this expansion is so rapid, any attempt by inflation to end everywhere at once fails. Regions where inflation persists grow faster than regions where it stops. Inflation wins by sheer volume. This is why it is called eternal. Not because it lasts forever in time necessarily, but because it never fully ends. There is always some region still inflating. Within this framework, the Big Bang becomes a local phenomenon. It is not the birth of space-time, but the birth of a particular space-time region with its own properties. The laws of physics inside a bubble universe may differ slightly from those in another. Constants may vary. Dimensions may behave differently. Even the nature of particles could change. This leads to an unsettling but powerful implication. The laws of physics we observe may not be unique or inevitable. They may be environmental. We see them because we exist in a region where they allow complex structures to form. And that brings us uncomfortably close to the idea that our universe is just one outcome among many, not selected by design but by circumstance. We are here because we can be here. Eternal inflation does not claim that this is satisfying. It simply follows the mathematics to its conclusion. And the conclusion is vast. Time in this picture becomes layered. Within each bubble universe, time begins at its Big Bang and flows forward, shaped by entropy and expansion. But in the inflating background, time may behave differently. It may not have a clear beginning or end. It may stretch indefinitely, spawning universes without limit. This raises difficult questions about probability and prediction. If infinitely many universes exist, how do we make sense of likelihood? How do we define what is typical? These are not merely philosophical puzzles. They are technical challenges that cosmologists wrestle with intensely. Yet, despite these challenges, eternal inflation remains one of the most compelling ideas in modern cosmology. Not because it answers all questions, but because it connects many threads: quantum fluctuations, vacuum energy, inflation, the Big Bang. They come together in a single, if dizzying, picture. It also reframes the question of what was before the Big Bang. The answer becomes contextual. Before our Big Bang, there was an inflating space-time. But before inflation itself, we do not yet know. The question retreats, always one step ahead, inviting deeper theories. And perhaps that is fitting. Each time we think we have reached the foundation, another layer appears beneath our feet. There is also something quietly humbling about eternal inflation. It suggests that our universe is not the stage on which everything happens. It is one story among countless others, each unfolding beyond the reach of observation. The cosmos becomes less like a single narrative and more like a library, filled with books we will never read. And yet, we should be careful. Eternal inflation is a hypothesis, not a fact. It rests on extrapolations of known physics into regimes we cannot yet test directly. Some physicists are uneasy with its implications. Others see no alternative. The debate is ongoing, vibrant, unresolved. But regardless of where the truth lies, the idea leaves a lasting impression. It invites us to loosen our grip on the notion of a singular beginning. It asks us to imagine reality as something far larger, far older, far more prolific than we once thought. And once we accept that, another idea slips naturally into view. If inflation can give rise to countless bubble universes, each with its own Big Bang, then perhaps we should speak not of one universe, but of many. A multiverse, not as science fiction, but as a serious consequence of our best theories. And that thought, vast and slightly unsettling, draws us onward into the next stage of our exploration, where Big Bangs themselves become commonplace, and our universe takes its place among an unimaginable multitude. And so, once we allow the idea of eternal inflation to settle, something even more expansive quietly unfolds before us. If inflation never truly ends, if it continues in some regions while stopping in others, then the natural consequence is unavoidable. There is not just one Big Bang. There are many, perhaps endlessly many. Each one marks the birth of a universe unto itself, sealed off from the others, drifting away faster than light can ever hope to cross the distance between them. And in that realization, the word universe begins to feel strangely insufficient. You see, what we have been calling the universe may only be our local domain. Our observable cosmos, bounded by the distance light has been able to travel since our own Big Bang, is just one region where inflation ended in a particular way. Beyond that horizon, there may be other regions, each born from their own Big Bang, each unfolding with its own history, its own laws, its own sense of time. This is the heart of the multiverse idea. Not as a whimsical invention, not as a poetic metaphor, but as a direct implication of theories we already take seriously. Eternal inflation does not politely stop at producing one universe. It keeps going. And every time inflation ends in a localized region, a new universe is born. Our universe, then, is one bubble among countless others, floating in a vast, inflating background. These bubbles do not collide easily. Space between them expands so rapidly that they are effectively isolated forever. Each bubble carries its own space-time, its own beginning, its own arrow of time. And this changes the meaning of existence in a profound way. For centuries, we have slowly been removing ourselves from the center of things. Earth is not the center of the solar system. The sun is not the center of the galaxy. The Milky Way is not the center of the universe. And now, perhaps, our universe itself is not the whole of reality. It is just one of many. In this picture, each Big Bang is not a universal beginning, but a local event, a phase transition, a bubble nucleation. From inside each universe, the Big Bang looks like the origin of everything. Space expands, time begins, matter forms. But from the outside, if such a perspective even makes sense, it is simply one event among countless others in a larger structure. And here, we must tread carefully, because language struggles again. What is this larger structure? It is not space as we know it. It is not time as we experience it. Some physicists refer to it as a higher dimensional space-time, or a metaspace, a background in which bubble universes are embedded. But these words are placeholders, not explanations. What matters is the idea that our universe may not be unique in its existence, nor even in its laws. In some multiverse models, different universes can have different values of fundamental constants. The strength of gravity may vary. The masses of particles may differ. The number of dimensions may not be the same. Even the basic structure of physical law could shift from one universe to another. This is not an arbitrary claim. Many theories that attempt to unify physics at the deepest level, particularly those involving extra dimensions, allow for a vast landscape of possible solutions. Each solution corresponds to a different set of physical laws. Eternal inflation provides a mechanism to realize many of these possibilities, each in its own universe. And once this door is opened, a curious shift occurs in how we think about explanation. Instead of asking why the laws of physics are the way they are, we may be forced to ask why we find ourselves in a universe with these laws. The answer may be unsettlingly simple, because only in such a universe could observers arise. This idea, known as anthropic reasoning, is often misunderstood. It does not say that the universe was designed for life. It says that among many possible universes we can only observe those compatible with our existence. We should not be surprised to find ourselves in a universe where stars form, chemistry works, and complexity can emerge. If it were otherwise, we would not be here to notice. This line of thought makes some physicists deeply uncomfortable. It feels like giving up, like replacing explanation with selection. And yet, if the multiverse is real, anthropic reasoning may be unavoidable. It becomes a filter, not a cause. But before we dismiss or embrace this too quickly, we should pause and consider the limits of what can be tested. One of the most serious criticisms of the multiverse is that other universes may be forever beyond observation. If they cannot be seen, measured, or influenced, can they truly be said to exist in a scientific sense? This is not a trivial objection. Science relies on evidence. Yet science has also always dealt with unobservable entities, fields, forces, space-time curvature, quarks. What matters is not direct observation, but whether a theory that includes such entities makes testable predictions. In the case of the multiverse, the hope is that traces of its existence might be indirectly observable. For example, if our bubble universe collided with another early in its history, that collision might leave an imprint in the cosmic microwave background. Subtle patterns, anomalies, cold spots. So far, no definitive evidence has been found, but the search continues. There are also statistical arguments. If a theory predicts a multiverse and also successfully explains the properties of our universe, that may count as indirect support. But this is a subtle and contentious area. The line between physics and philosophy becomes blurred, and perhaps that is inevitable. The multiverse pushes us to the edge of what science can comfortably address. It forces us to confront questions about existence itself, about what it means to say that something is real. Still, even if the multiverse remains untestable in practice, its conceptual impact is immense. It reframes the Big Bang not as a singular cosmic event, but as a common occurrence, a natural outcome of deeper processes. Big Bangs may be happening all the time, in regions forever hidden from us. This also reshapes our sense of cosmic history. Our universe has a past stretching back to its own Big Bang. But beyond that, there may be a much larger history, one that does not belong to any single universe, a history of inflating space, spawning universes again and again. Time in this larger picture becomes deeply strange. Within each universe, time has a beginning and flows forward. But in the multiverse as a whole, time may be endless, or it may not even be meaningful in the same way. The concept of before and after may only apply locally. And notice how this echoes earlier themes. Time emerging rather than existing absolutely, beginnings as local phenomena rather than global ones, the universe as a process rather than a thing. The multiverse also invites a certain humility. If countless universes exist, then our own is not privileged by its existence. It is special to us, of course. It is our home. But cosmically, it may be one among many, distinguished not by destiny, but by circumstance. And yet, there is something deeply human about grappling with this idea. We have always wondered whether we are alone, first as individuals, then as a species, then as a planet. Now, perhaps, as a universe. Are we alone in reality itself? The multiverse does not answer this question in a comforting way. It suggests abundance rather than uniqueness, proliferation rather than singularity. Reality may be far more generous and far less personal than we would like. Still, abundance does not strip meaning. Meaning is something we create, something that arises from relationships, from consciousness, from experience. Even if there are infinitely many universes, this one matters, because it is the one in which we exist. And as we sit with that thought, another idea quietly begins to shimmer at the edge of our imagination. If universes can differ so radically from one another, if reality can take so many forms, then perhaps our own universe is not fundamental in another sense as well. Perhaps it is not even base reality. Perhaps it is a constructed layer, a representation, a computation. What if the laws of physics we observe are not the deepest laws? What if they are the rules of a system, running on something more fundamental still? And with that gentle, unsettling possibility, our journey naturally drifts onward, away from the multiplicity of universes, toward an idea that challenges not just cosmology, but the very nature of reality itself. And so, having wandered through a reality crowded with universes, each born of its own Big Bang, each sealed away in its own expanding bubble, we arrive at a question that feels almost inevitable. If there are many universes, if laws can vary, if existence itself seems less absolute than we once believed, then what if even space-time is not the deepest layer of reality? What if the universe we experience is not fundamental at all, but constructed? What if reality at its core is more like a process than a place? And here, quietly, but profoundly, the simulation hypothesis enters the story. You see, this idea does not arise from science fiction alone, though it has certainly captured the imagination of storytellers. It emerges from a convergence of several lines of thought in physics, information theory, and computation. As we probe deeper into the structure of reality, we find that the universe behaves less like a collection of solid objects and more like an unfolding computation, discrete units, quantized interactions, information flowing, being transformed, conserved, erased. At the smallest scales we can describe, nature appears digital rather than continuous. Energy comes in packets. Information has limits. There is a smallest meaningful length, a smallest meaningful time. Space and time themselves may be granular, pixelated in a sense, though far beyond anything we could ever see directly, and that begins to sound uncannily like a simulation. In this view, the universe is not built from matter in the traditional sense. It is built from information. Physical laws become rules of processing. Particles become excitations of underlying fields. Reality becomes something that runs. Now, before this idea feels too abstract, let us ground it in something familiar. We already create simulations. Crude ones, yes, but increasingly sophisticated. We simulate weather systems, ecosystems, galaxies. We model neural networks that learn and adapt. As computing power grows, these simulations become more detailed, more lifelike. It is not unreasonable to imagine that a sufficiently advanced civilization could simulate entire universes, complete with conscious observers. And here comes the unsettling part. If such simulations are possible, and if they are run many times, then statistically, simulated observers would vastly outnumber observers in a base reality. If that is the case, then any randomly selected conscious being is more likely to exist inside a simulation than outside it. This is not a claim about technology. It is a logical argument about numbers. And once you see it that way, the simulation hypothesis stops sounding like science fiction and starts sounding like an uncomfortable probability problem. In this picture, the Big Bang takes on a radically different meaning. It is not the birth of reality. It is the initialization of a system. The moment the simulation starts running, space and time come into existence not because they were created from nothing, but because the program began. Before the Big Bang, then, there was no space-time within the simulation. But there may have been something else entirely, a higher level of reality, a computational substrate, a realm where time flows differently, or perhaps not at all, relative to the simulated universe. The laws of physics we observe become constraints of the system, limits on processing speed, limits on information density. The speed of light, for example, could be a maximum rate of information transfer. Quantum randomness could be genuine randomness, or it could be pseudo-randomness, indistinguishable from the inside. Even the apparent fine-tuning of the universe takes on a new light. Instead of asking why constants have life-permitting values, we might ask why the simulation was configured that way, or whether many configurations exist, with ours simply being one that supports complex structures. This idea is deeply controversial, and rightly so. It challenges the foundations of scientific realism. It raises questions that may be impossible to test conclusively. And yet, it persists, because it resonates with patterns we already see. The universe is astonishingly mathematical. Simple equations describe vast swaths of reality. Symmetries govern interactions. Information appears to be conserved in deep and surprising ways. Black holes, for instance, behave like thermodynamic systems. They have entropy. They encode information on surfaces, not volumes. Reality seems to care deeply about bookkeeping. All of this suggests that information is not just a tool we use to describe the universe. It may be what the universe is made of. In a simulated universe, this makes perfect sense. Information is fundamental. Everything else is emergent. Now, does this mean that the universe is literally running on a computer as we understand computers? Probably not. The metaphor breaks down quickly if taken too literally. Whatever underlies our reality, if anything does, may be so different from our technology that the word computer becomes misleading. But the core idea remains. Our universe may be a layer, a representation, a projection of something more fundamental. And here, perhaps, we should pause and ask what this would mean for us. If we live in a simulation, does that make our experiences less real? Does it strip meaning from our lives? Does it reduce love, beauty, curiosity to lines of code? I would argue the opposite. Reality is defined by experience. Pain hurts whether simulated or not. Joy feels joyful regardless of the underlying substrate. Meaning arises from relationships, from consciousness reflecting on itself, not from the ultimate nature of the hardware. If anything, a simulated universe would be no less wondrous. It would be more so, because it would mean that layers of reality exist, stacked like Russian dolls, each giving rise to the next. And perhaps that layered structure is already hinted at in physics. We speak of effective theories. Each level of description works within a certain range. Atoms emerge from quantum fields. Chemistry emerges from atomic interactions. Biology emerges from chemistry. Consciousness emerges from neural activity. At no point do we find a single level that explains everything in isolation. Why should the universe itself be different? Still, the simulation hypothesis remains deeply contentious because it is difficult to falsify. Any observation we make could, in principle, be part of the simulation. Glitches, discreteness, apparent limits could be interpreted as evidence, but could also be explained by ordinary physics. Some have suggested searching for computational artifacts, preferred reference frames, anisotropies, limits to complexity, but so far, nothing definitively points to a simulated reality rather than a fundamental one. And perhaps that is telling. Perhaps the hypothesis is not meant to be proven or disproven, but to force us to rethink our assumptions, to question what we mean by real, to notice how deeply we equate existence with fundamentality. In the context of our larger journey, the simulation idea offers yet another answer to the question of what was before the Big Bang. Before our Big Bang, there may have been a different level of reality altogether. Not a previous universe in space-time, but a context in which space-time itself is generated. This mirrors themes we have seen again and again. The Big Bang as a local beginning, time as emergent, reality as layered, whether through cyclic universes, quantum vacuums, inflationary backgrounds, or computational substrates, the story keeps repeating. What we take to be fundamental turns out to be contingent. And notice how each of these ideas, wildly different on the surface, converge on a similar intuition. The universe we see is not the whole story. It is a chapter, not the book. The simulation hypothesis also blurs the line between physics and philosophy. It forces us to confront questions about consciousness, about observation, about what it means to know something. If reality is constructed, then knowledge itself becomes part of the construction, and that naturally leads us toward an even deeper shift. If information is fundamental, if reality is encoded rather than built, then perhaps matter and space-time are not primary at all. Perhaps the deepest layer of existence is not substance, but information itself. Bits rather than things. Patterns rather than particles. And with that quiet but radical idea, our path bends once more, away from simulations and substrates, toward a vision of the universe where everything, from particles to people to galaxies, emerges from pure information, waiting to be decoded. And so, as the idea of simulation gently fades into the background, leaving us with the unsettling sense that reality may be layered rather than absolute, another perspective begins to crystallize, one that feels, somehow, both more abstract and more intimate. If the universe can be simulated, if it can be computed, if it can be encoded, then perhaps computation is not merely a metaphor. Perhaps it is a clue. Perhaps information itself is the deepest currency of reality. You see, over the past century, physics has been quietly transforming its language. Where once we spoke primarily of matter and force, we now increasingly speak of states, correlations, probabilities, and bits. In quantum mechanics, the state of a system contains all that can be known about it. In thermodynamics, entropy measures information we lack about microscopic details. In black hole physics, the most extreme environments we know, entropy scales not with volume, but with surface area, as if reality itself is keeping a ledger of information on cosmic boundaries. And that is not a coincidence. The idea that information is fundamental did not emerge overnight. It grew slowly from scattered insights that, taken together, point toward a profound shift in how we understand existence. One of the earliest hints came from the realization that information is physical. This is not poetry. It is a precise statement. To erase information requires energy. To store information requires a physical system. Information is not an abstract add-on to reality. It is embedded within it. From this perspective, particles are not tiny billiard balls. They are carriers of information. Fields are not substances filling space. They are rules governing how information propagates. Even space-time itself may be a way of organizing relationships between bits of information. So when we ask, what was there before the Big Bang, a new answer quietly suggests itself. Perhaps there was information, not matter, not energy, not space or time, but raw informational structure, patterns without a stage, potential without form. This is a difficult idea to grasp because we are accustomed to information being about something, a message, a signal, a description. But at the deepest level, information may not describe reality. It may constitute it. In some approaches to quantum gravity, space-time is not fundamental. It emerges from entanglement, from relationships between quantum degrees of freedom. Distance becomes a measure of how strongly systems are correlated. Geometry becomes an expression of information flow. The fabric of the universe is woven not from threads of space, but from threads of correlation. And that changes everything. In such a universe, the Big Bang is not the moment when matter appeared. It is the moment when information became organized in a particular way. A decoding. A transition from a compact, highly compressed informational state into an expanding, unfolding structure where information could differentiate, diversify, and complexify. Before the Big Bang, then, there may have been no particles, no fields, no space-time. But there may have been information in a pure, undifferentiated form, a kind of cosmic code, waiting not to be created, but to be expressed. This resonates deeply with what we see in the early universe. The cosmos begins in a state of astonishing simplicity, almost perfectly uniform. Tiny fluctuations, barely noticeable, are all that break the symmetry, and yet from those fluctuations everything else grows. Galaxies, stars, planets, life, thought, meaning. It is as if the universe began as a compressed file, containing vast complexity and latent form, then gradually decompressed over billions of years. Entropy plays a central role here. Often misunderstood as disorder, entropy is better thought of as missing information. It measures how many microscopic arrangements correspond to the same macroscopic appearance. As the universe expands, entropy increases. Information spreads out. The universe explores more of its possible states. And crucially, the arrow of time appears to be tied to this process. Time flows in the direction of increasing entropy, in the direction of information dispersal. In this view, time is not fundamental either. It is a consequence of how information changes. If that is true, then before the Big Bang, when information was maximally compressed, time may not have existed in any meaningful sense. No sequence, no flow. Just a static informational structure, or perhaps something even stranger, where change itself was undefined. The Big Bang becomes the moment when time begins, because it is the moment when information begins to differentiate. When there is a before and after because there is something to distinguish one state from another. This idea also sheds light on the deep connection between quantum mechanics and information. Quantum states encode probabilities. Measurement extracts information. Entanglement links distant systems in ways that defy classical intuition. Information seems to ignore space-time boundaries, hinting that space-time may not be the primary arena after all. Black holes sharpen this insight dramatically. When matter falls into a black hole, its information does not disappear. That would violate the fundamental rules of quantum mechanics. Instead, the information is somehow preserved, encoded on the event horizon. A two-dimensional surface contains all the information about a three-dimensional region. This is not how we expect reality to behave, and yet it appears to be true. This leads to the holographic principle, the idea that the universe may be describable as information encoded on a lower dimensional boundary, reality as a projection, not in the sense of illusion, but in the sense of representation. And once again, the theme returns. Layers, encodings, emergence. If the universe is fundamentally informational, then matter and energy are secondary. They are ways information manifests at scales we can perceive. The laws of physics become transformation rules. They tell information how it can change, how it can move, how it can combine. This perspective also reframes the question of origin. Information does not need to be created in the way matter does. It can exist as structure, as possibility. The question shifts from why does something exist to why does information take this form rather than another? And perhaps that question is not answered by causation, but by consistency. Certain informational structures may be self-sustaining. They may give rise to stable patterns. They may generate observers capable of reflecting on them. In this view, the universe exists because it is a consistent informational system, one that allows complexity to emerge, one that does not contradict itself, one that can unfold without collapsing into paradox. This idea has a strange, almost Platonic flavor. Reality as mathematics, existence as consistency, the universe not as a thing, but as a theorem. And yet, despite its abstraction, this perspective remains grounded in physics. It arises from attempts to reconcile quantum mechanics, gravity, thermodynamics, and cosmology. It is not mysticism. It is an honest response to the patterns we observe. Still, there are deep challenges. What exactly is information without a physical substrate? Can information exist without time, without space, without energy? These questions push us to the limits of what we can even articulate, but perhaps that is the point. When we ask about before the Big Bang, we are not merely asking a scientific question. We are probing the boundaries of thought itself. We are testing how far our concepts can stretch before they lose meaning. The informational universe does not give us a comforting answer. It gives us a quieter one. Before the Big Bang, there may have been no things, no events, no moments. But there may have been structure, potential, a logical space of possibilities from which our universe emerged as one consistent realization. And notice how this connects back to everything we have explored. Cycles, vacuums, inflation, multiverses, simulations. Each in its own way suggests that the universe we see is not fundamental. Each points toward a deeper layer where familiar categories dissolve. Information may be that layer, or it may be a stepping stone toward something even deeper. And as we approach that depth, another realization begins to surface. For all our theories, all our models, all our elegant ideas, we are still constrained by what we can observe, measure, and test. There are limits not just to technology, but to knowledge itself. Perhaps the universe before the Big Bang is not silent because there was nothing there, but because we do not yet have the language to hear it. And with that thought, heavy with both wonder and humility, we find ourselves naturally approaching the next chapter of this journey. A chapter not about what might exist beyond our universe, but about the boundaries of science itself, about what we can know, what we cannot, and why the universe sometimes answers our questions with silence. And so we arrive, almost inevitably, at a quieter place in this journey. After roaming through eternal universes, quantum vacuums, inflating backgrounds, multiverses, simulations, and realities built from information, we begin to sense a boundary. Not a boundary in space, not even one in time, but a boundary in understanding itself. Because no matter how imaginative our theories become, they are still constrained by something deeply human: the limits of science. You see, science is an extraordinary tool, but it is not an all-seeing eye. It is a method, a way of asking questions about nature that relies on observation, measurement, and testable prediction. And this method, powerful as it is, has edges. When we ask what existed before the Big Bang, we are pressing directly against those edges. One of the most fundamental limitations lies in the theories we use. Today, our understanding of the universe rests on two great pillars. General relativity describes gravity, space, and time on the largest scales. Quantum mechanics governs the behavior of matter and energy on the smallest scales. Each theory works astonishingly well in its own domain. Each has been tested to extraordinary precision, and yet they do not fit together. When we try to apply general relativity to the very early universe, to the moment we call the Big Bang, it predicts a singularity, a point where density becomes infinite, curvature becomes infinite, and the equations themselves lose meaning. This is not a physical prediction in the usual sense. It is a sign of breakdown, a warning that the theory is being pushed beyond where it can be trusted. At the same time, quantum mechanics tells us that infinities of this sort are unphysical. Nature, at the smallest scales, resists infinite quantities. It becomes fuzzy, probabilistic, discrete, and yet we do not have a complete theory that combines quantum mechanics with gravity. We do not yet possess a theory of quantum gravity. This absence is not a minor technical gap, it is a fundamental limitation. Without a working theory of quantum gravity, we cannot reliably describe what happens at the very beginning of the universe. We can extrapolate, we can speculate, we can propose models, but we cannot confirm them. And that is a humbling realization. The Big Bang, then, is not just an event in cosmic history, it is a mathematical wall. When we run our equations backward in time, everything works beautifully until we reach a certain point. Then suddenly, the symbols stop corresponding to anything physical. Time appears to end. Space collapses into a point. And the theory goes silent. This silence does not mean there was nothing. It means we do not know how to listen. There is another, more practical limitation as well. Even if we had the perfect theory, observation itself has limits. Light travels at a finite speed. The universe has a finite age since the Big Bang phase we can observe. This creates a cosmic horizon. Beyond a certain distance, signals simply have not had time to reach us. When we look out into space, we are also looking back in time. The farther we look, the earlier the epoch we see. Eventually, we reach a time when the universe was so hot and dense that light could not travel freely. Before that moment, the universe was opaque. No electromagnetic signal can carry information from earlier times to us. The cosmic microwave background marks this boundary. It is the oldest light we can observe. Beyond it, the universe is hidden, not because it did not exist, but because it was unreadable. And even before that, there is a deeper limit. The Planck time. A tiny fraction of a second after the Big Bang. Earlier than this, our concepts of space and time themselves break down. Quantum fluctuations of space-time become dominant. Distances and durations lose their usual meaning. This is not just a technological limitation. It is a conceptual one. We do not know how to describe physics beyond this point. Our language fails. Our mathematics becomes unreliable. So when we ask what happened before the Big Bang, we must recognize that we are asking a question that may not be answerable in the usual scientific sense, not yet, and perhaps not ever. And this is where science does something quietly courageous. It admits ignorance. Science does not fill gaps with certainty. It marks them. It draws a line and says, we do not know what lies beyond this point. That admission is not weakness. It is integrity. This is especially important because the temptation to overreach is strong. When faced with silence, the human mind wants to speak anyway. It wants stories. It wants explanations. It wants closure. But science resists that urge. It prefers honest uncertainty to confident fiction. This does not mean that speculation is forbidden. On the contrary, speculative models drive progress. Eternal inflation, cyclic universes, quantum creation, informational reality. All of these ideas are valuable. They explore the space of possibilities. They stretch our imagination. They may one day become testable, but for now they remain hypotheses, not conclusions. And that distinction matters. Another limitation of science lies not in the universe, but in us. Our brains evolved to survive on the savannah, not to intuit quantum space-time. Our intuitions are shaped by everyday scales. We are comfortable with solid objects, continuous time, simple causality. The universe, at its deepest levels, is none of these things. When physics tells us that time may emerge, that space may be relational, that causality may be local rather than global, it is not surprising that we struggle. The problem is not that the universe is illogical. It is that our intuition is parochial. Mathematics helps us go beyond intuition, but mathematics too has limits. Equations are symbols. They represent structures. They require interpretation. And sometimes different interpretations lead to radically different pictures of reality, all consistent with the same data. This is why cosmology often feels philosophical. We are not just testing hypotheses. We are choosing frameworks. We are deciding which questions are meaningful. And here, the question of before the Big Bang reveals its true nature. It may not be a question about history. It may be a question about language. If time itself emerges with the Big Bang, then the word before may not apply. If causality is defined within space-time, then asking for a cause of space-time may be incoherent. Not false. Incoherent. This is deeply unsettling because it suggests that some questions we instinctively ask are not wrong, but misplaced, like asking what sound a color makes. And yet the human impulse to ask them is not misguided. It reflects curiosity, wonder, a refusal to accept the visible surface as the whole story. Science thrives on that impulse, but it also disciplines it. There is another, quieter limit that deserves attention. Even if we could, in principle, know what existed before the Big Bang, would that knowledge change anything about how the universe behaves? Now, would it alter the laws of physics? Would it change our daily experience? Perhaps not. And that raises a subtle question. Is every question worth pursuing scientifically? Or are some questions meaningful in other ways? Science is extraordinary at telling us how things work. It is less equipped to tell us what they mean. When we ask about the origin of existence, we are often asking both at once, without realizing it. We want a cause, but we also want significance. When science answers with silence, it may be because significance is not something the universe hands us. It is something we bring. And notice how this does not diminish science. It clarifies its role. Science tells us that we do not yet have a complete theory of quantum gravity, that our equations break down at the Big Bang. That observation cannot peer beyond certain limits, that some questions may be ill-posed within our current frameworks. What science does not tell us is that curiosity is futile, or that mystery is failure. On the contrary, mystery is the engine of progress. Every time science has encountered a boundary, that boundary has eventually shifted. Atoms were once unknowable. Stars were once unreachable. The age of the universe was once a matter of guesswork. Each silence eventually gave way to understanding. But there is no guarantee that all silences will. The universe does not promise to be fully intelligible to creatures like us. It may contain aspects forever beyond our reach, not because they are hidden, but because we are limited. And that realization, far from being depressing, can be profoundly liberating. It invites humility. It tempers certainty. It reminds us that knowledge is not possession, but participation. We are part of the universe trying to understand itself, using tools that evolved within it. That alone is astonishing. So when we stand before the Big Bang and hear nothing, perhaps we should not rush to fill the silence. Perhaps we should listen to it. The silence may be telling us that the question of before is not just about physics. It is about how we frame existence, about whether reality requires a starting gun, about whether becoming is more fundamental than beginning. And here, gently, the journey begins to turn once more, away from equations and observations and toward reflection, toward philosophy, toward ancient and modern ways of thinking about existence that do not demand a first moment, but see reality as a process, a flow, a potential unfolding without absolute origin. If science tells us where its limits lie, philosophy asks what those limits mean. And so, from the quiet boundary of what we can know, we step naturally into the next chapter, one that asks not what existed before the Big Bang, but what existence itself requires, and whether the universe needs a beginning at all. And so, having reached the quiet edge where science itself pauses and admits its limits, we find ourselves stepping into a different landscape altogether. Not one ruled by equations or observations, but by questions that have followed humanity for as long as we have been able to think at all. Questions about existence, about cause, about whether reality needs a beginning in the first place. And this is where philosophy, ancient and modern, begins to speak in a softer but no less profound voice. You see, when we ask what was before the Big Bang, we often assume that existence must have a cause, that something must come from something else. This assumption feels so natural that we rarely notice it. Every object we encounter has an origin. Every event has a prior condition. Every story has a first chapter. But philosophy gently asks us to examine whether this way of thinking applies to reality as a whole. Does existence itself require a cause? In everyday life, causality is indispensable. It helps us navigate the world. We learn that touching fire causes pain, that planting seeds leads to growth, that actions have consequences. But causality, like time, may be a local rule rather than a universal one. It may operate within the universe, not outside it. If the universe contains all that exists, then what could possibly cause it? A cause, by definition, would have to exist outside the universe. But outside of everything is a phrase that strains meaning. Perhaps it is not that the universe has an unknown cause. Perhaps the demand for a cause simply does not apply. This idea is deeply unsettling, especially to minds trained in scientific explanation. We want reasons, we want mechanisms, we want chains of logic that stretch backward until they reach a firm anchor. But philosophy reminds us that not all questions have answers of the same kind. Some traditions, particularly in Eastern philosophy, have long embraced this perspective. In certain strands of Buddhist thought, for example, reality is not seen as a created object, but as a process, a continual becoming. There is no first moment because there is no static thing that begins. There is only change, arising from conditions, dissolving into new conditions, without a fixed origin point. Similarly, in Taoist philosophy, the Tao is not something that began. It is the way things unfold. Asking when it started is like asking when flow began. The question misunderstands the nature of what is being described. And when you look at modern physics through this lens, something curious happens. The universe begins to look less like an object and more like a process. Space and time emerge. Particles appear and disappear. Fields fluctuate. Information reorganizes itself. Nothing stands still. Everything is becoming. In this view, the Big Bang is not the beginning of existence, but a transition within an ongoing process, a moment when the universe entered a new mode of being, a phase change, not a creation event. This resonates strongly with what science itself suggests. We have seen again and again that the Big Bang may not be an absolute origin. It may be preceded by inflation, by quantum states, by informational structures, or by something we cannot yet describe. Each model replaces the idea of creation with the idea of transformation. Philosophy invites us to take that replacement seriously. Another deeply philosophical question arises here. Must existence have a reason at all? We often assume that everything must be explainable, that there must be a why behind every fact. But some philosophers argue that existence may simply be a brute fact, not because we are lazy, but because explanation itself has limits. At some point, any chain of explanation must stop. If you ask why endlessly, you eventually reach a place where the answer is, that is just how it is. The laws of logic, the axioms of mathematics, the existence of existence. This does not mean that inquiry is meaningless. It means that meaning does not always come from explanation. And perhaps this is where the question of before the Big Bang reveals something about us rather than the universe. We ask it because we are uncomfortable with ungrounded existence. We want reality to stand on something firm. But maybe reality does not need to stand on anything at all. In some philosophical traditions, existence is seen not as a thing that needs justification, but as a field of potential. Before forms arise, there is potentiality. Not nothing, but not something either. A state of readiness, of possibility. This aligns intriguingly with some modern interpretations of quantum physics, where systems exist in superpositions until observed, where outcomes are potentials rather than certainties. Before the Big Bang, there may have been no definite universe, but a state of pure potential from which many outcomes were possible. The Big Bang, then, becomes the moment when potential crystallized into actuality. Not the creation of being from non-being, but the selection of one path among many. This idea dissolves the sharp boundary between before and after. Before the Big Bang, reality may not have been temporal in the way we understand time. It may have existed as a timeless potential. Asking what happened then may be like asking what a melody sounded like before it was played. The melody existed as structure, as possibility, but not as sound. And notice how gently this reframes the problem. The universe does not come from nothing. It comes from possibility. And possibility does not need a cause. It is simply the space of what can be. This perspective also echoes certain Western philosophical ideas. Aristotle spoke of potentiality and actuality as fundamental aspects of being. Things exist first as potentials, then as realized forms. Applied to the universe itself, this suggests that existence may not require a first cause, only a transition from potential to actual. More recently, some philosophers of science have argued that time itself may be an emergent feature of a deeper, timeless reality. In such a framework, asking what happened before time began is like asking what happened north of the North Pole. The question assumes a dimension that does not exist at that level, so perhaps the deepest philosophical answer to what was before the Big Bang is not another event, not another universe, not another state in time, but a different mode of being altogether. And here, the humility we encountered in science returns, now enriched by reflection. We may never know what that mode of being was. We may never have the language to describe it. Our concepts are forged in time, in change, in causality. They may simply not apply. But that does not mean the question is meaningless. On the contrary, it may be one of the most meaningful questions we can ask, precisely because it reveals the boundaries of thought. There is also a deeply human aspect to this inquiry. When we ask about the beginning of the universe, we are often, perhaps unconsciously, asking about our own beginnings, about whether our lives have meaning in a universe without a starting point, about whether purpose requires origin. Philosophy suggests that it does not. Meaning is not bestowed by beginnings. It is created by experience, by consciousness reflecting on itself, by relationships, creativity, curiosity, and care. Whether the universe had a beginning or not, we still find ourselves here, capable of wonder. And perhaps that is the most extraordinary fact of all. The universe, however it came to be, has produced beings who can ask how it came to be. It has generated questions about its own origin. In that sense, the universe is not silent. It is thinking through us. When we stand at the edge of the Big Bang and peer into the unknown, we are not just explorers of the cosmos. We are participants in its unfolding. Our questions are part of its story. Philosophy does not replace science. It complements it. Where science tells us how far our knowledge can reach, philosophy asks what that reach means. Where science draws boundaries, philosophy reflects on why they are there. And as we move forward from this chapter, one final realization begins to form. The question of what was before the Big Bang may not have a single answer. It may not even have a correct form. But asking it has value nonetheless, because it teaches us humility. It teaches us patience. It teaches us that the universe does not owe us simplicity, and that understanding is not always about closure, but about openness. And so, having explored science, speculation, and philosophy, we find ourselves ready for the final step of this journey, not toward an answer, but toward a choice about how we, as a species, should live with unanswered questions, whether we should insist on certainty or learn to dwell comfortably in mystery. And that, gently, brings us to the last open horizon. The question not of what was before the Big Bang, but of whether we truly need that answer at all, and what it means for the future of human understanding if we never find it. And so, after wandering through science, speculation, and philosophy, after standing at the boundary where equations fall silent and concepts begin to blur, we arrive at a space that feels both uncertain and strangely familiar, a space not of answers, but of open questions, questions that do not demand resolution, but invite reflection. And perhaps that, you see, is where the journey was always leading. At this point, it becomes reasonable to ask something quietly radical. Do we actually need an absolute answer to what was before the Big Bang? Or is the desire for such an answer revealing more about the human mind than about the universe itself? For much of our history, knowledge has advanced by replacing mystery with explanation. Thunder became electricity. Disease became biology. The motion of the heavens became gravity. Each time uncertainty retreated and confidence grew. It is tempting, then, to believe that every question must eventually yield to the same process, that one day, with enough intelligence and enough technology, the universe will finally confess its deepest secret. But perhaps that expectation is itself a kind of illusion. The question of before the Big Bang may not be like other questions. It may not be a puzzle waiting patiently for the right solution. It may be more like a mirror, reflecting the limits of our cognition, the structure of our language, and the assumptions we carry without noticing. We are biological beings, shaped by evolution to navigate a world of causes and effects, beginnings and endings. Our brains are storytellers. We make sense of reality by arranging events into narratives, but the universe may not be obliged to conform to narrative logic. It may not have a beginning in the way stories do. Or if it does, that beginning may not be accessible to beings like us. This raises a deeper issue: the limits of human cognition. Our sensory systems evolved to detect food, danger, and shelter, not quantum gravity or timeless states of existence. Our intuitions are reliable at human scales and deeply unreliable beyond them. Even mathematics, our most powerful extension of thought, relies on axioms that we accept without proof. Every system of knowledge rests on something unexamined. So when we ask whether we should expect to understand what was before the Big Bang, we are really asking whether the universe is fully intelligible to minds like ours, and there is no guarantee that it is. This is not a pessimistic thought. It is a realistic one. The universe existed for billions of years before humans appeared. It will likely exist for billions of years after we are gone. Our presence is brief. Our perspective is narrow. Expecting total comprehension may be an act of hubris rather than curiosity. Yet, interestingly, this realization does not diminish science. It refines it. Science does not promise absolute truth. It promises progressively better models, approximations that work within certain domains, maps that capture some features of the territory while leaving others blank. The blank regions are not failures, they are invitations. Throughout this exploration, we have seen how many plausible ideas exist about what might have preceded the Big Bang: eternal universes, cyclic cosmologies, quantum vacuums, inflationary backgrounds, multiverses, simulations, informational substrates. Each is internally coherent. Each is motivated by serious reasoning. And yet, none is confirmed. This plurality of possibilities is not a weakness of cosmology. It is a reflection of where we stand in our understanding. We are at a frontier, and frontiers are uncomfortable places. They lack certainty. They lack closure. They force us to tolerate ambiguity, which brings us to another quiet question. Should we even be seeking an ultimate answer? The history of science suggests that progress often comes not from answering old questions, but from asking better ones. The Big Bang itself was not discovered by asking what existed before the universe, but by asking how galaxies move, how light travels, how matter behaves. The origin question emerged later, almost as a byproduct. It is possible that asking what was before the Big Bang is not the most fruitful question we can ask right now. It may be too vague, too dependent on assumptions about time, causality, and existence. The universe may be urging us gently to reframe the problem. Perhaps the more meaningful questions are these: what is time? What is information? What is space-time made of? How does reality organize itself? How does complexity arise? How does consciousness emerge? Answers to these questions may indirectly illuminate the origin problem, or they may render it obsolete. And notice how often in science old questions dissolve rather than get answered. We no longer ask what substance fire is made of. We no longer ask what pushes planets along their paths. Those questions were replaced by deeper frameworks that made the original formulations irrelevant. It is entirely possible that in the future, physicists will not ask what was before the Big Bang, because the framework in which that question makes sense will no longer exist. There is also the question of biological limits. Even if the universe is in principle intelligible, our species may not be capable of grasping it fully. Other intelligences, artificial or otherwise, may one day surpass us in their ability to model reality. They may see patterns we cannot. They may ask questions we cannot even formulate. And even then, they too may encounter limits. This is not defeat. It is perspective. Human knowledge has always grown within constraints. We cannot see ultraviolet light without instruments. We cannot hear radio waves without receivers. Our access to reality is mediated, indirect, incomplete. And yet, within those limits, we have built extraordinary understanding. Perhaps the correct attitude toward the origin of the universe is not insistence, but patience. Patience with unanswered questions. Patience with incomplete theories. Patience with silence. There is a tendency, especially in modern culture, to equate uncertainty with weakness, to believe that not knowing is a problem to be fixed as quickly as possible. But uncertainty can be fertile. It keeps inquiry alive. It prevents dogma. It reminds us that the universe is larger than our current explanations, and that brings us to humility. If there is one lesson that echoes through every serious attempt to understand the cosmos, it is this: the universe is not obliged to make sense to us, and yet, astonishingly, it often does. We have deciphered the life cycles of stars. We have traced the expansion of space. We have detected ripples in space-time itself. We have reconstructed the history of the universe back to its earliest observable moments. This alone is miraculous. That we cannot go further, for now, is not a failure. It is a boundary marker. The silence before the Big Bang may be telling us something essential. Not that there is nothing to know, but that knowledge itself has horizons. And perhaps at the deepest level, the question of before the Big Bang is not about cosmology at all. It is about how we relate to mystery. Do we demand certainty even when none is available? Or do we learn to live with openness, with curiosity, unaccompanied by closure. Science at its best does the latter. It advances by embracing the unknown, not denying it. The future of physics may eventually transform our understanding completely. A theory of quantum gravity may emerge. New observations may reveal unexpected structures. Concepts we take for granted may be replaced, and the question of before may look very different or disappear altogether, or it may remain forever unanswered. And that possibility should not frighten us, because the beauty of science is not only in the answers it provides, but in the questions it keeps alive, in the way it invites us to look beyond ourselves, to recognize our smallness without despair, to find meaning not in certainty, but in exploration. As we stand here at the edge of what can be known, the universe does not feel cold or indifferent. It feels vast, patient, willing to reveal some of its secrets while keeping others beyond reach. And maybe that balance is not accidental. Maybe the universe is not a riddle to be solved, but a conversation to be joined. A process we are part of, not spectators to. Our questions, our doubts, our wonder are themselves expressions of the cosmos reflecting on its own existence. If that is true, then asking what was before the Big Bang is already meaningful, regardless of whether it is ever answered. And as this journey gently loosens its grip on the need for final conclusions, another horizon quietly comes into view. A horizon not defined by time or space, but by awareness itself. Questions not about the beginning of the universe, but about the nature of consciousness, experience, and meaning within it. Because in the end, perhaps the most profound mystery is not what existed before everything, but how a universe capable of producing minds came to wonder about its own origin at all. And so, almost without noticing it, the question quietly transforms once again. We began by asking what existed before the Big Bang, as if we were standing outside the universe, peering backward into some hidden corridor of time. But now, after all these turns through science, philosophy, and humility, the question bends inward. It becomes less about what came before and more about who is asking. Because here we are, conscious beings, tiny arrangements of matter and energy on a small planet orbiting an ordinary star in a universe that may have no beginning we can name. And yet somehow, the universe has learned to look at itself through us. That alone is astonishing. You see, when we talk about the Big Bang, about quantum vacuums and information and timeless states, we often forget something essential. None of these ideas exist in the universe by themselves. They exist in minds. They are thoughts, interpretations, stories we tell in mathematics and language to make sense of patterns we observe. The universe does not ask what was before it. We do. And that realization opens a final, deeper layer of reflection. Perhaps the most profound mystery is not the origin of the cosmos, but the emergence of consciousness within it. The fact that the universe has produced observers capable of wondering about its own beginning may be more remarkable than any theory of creation. Consciousness is strange. We still do not understand how subjective experience arises from physical processes. We can map neural activity. We can correlate brain states with thoughts and emotions. But the inner glow of awareness, the feeling of being here, remains elusive. And notice how closely this mirrors the problem of the Big Bang. In both cases, we reach a boundary where explanation thins out. We can describe correlations. We can build models. But the deepest why seems to slip through our fingers. Some philosophers and physicists have suggested that consciousness may not be an accident, not a byproduct, but a fundamental aspect of reality in some form, not necessarily human consciousness, but the capacity for experience itself. If that is true, then the universe is not merely a machine that happens to produce minds. It is a system in which awareness is woven into the fabric, just as deeply as space, time, or information. This idea is controversial, of course. It challenges the traditional separation between observer and observed. But quantum mechanics already hints at this entanglement. Measurement matters. Observation changes outcomes. The line between subject and object becomes blurred. In that light, the question of what existed before the Big Bang takes on a new shade. Perhaps before the universe as we know it, there was not a thing, not a state, not even information in the usual sense, but a field of possibility that included the potential for awareness. Not awareness as we experience it, but the conditions under which experience could eventually arise. This is not something we can test. It may not even be something we can properly define, but it invites a shift in perspective. The universe may not be a cold, indifferent structure into which life accidentally stumbled. It may be a process that naturally gives rise to complexity, reflection, and meaning. And that does not require purpose in the traditional sense. It does not require design or intention. It requires only that the laws of reality allow self-organization, differentiation, and feedback. From that, stars form. From stars, elements. From elements, chemistry. From chemistry, life. From life, minds. And from minds, questions about beginnings. Seen this way, the Big Bang is not just the origin of space and time. It is the first step in a long chain that eventually leads to self-awareness. The universe unfolding into a state where it can contemplate itself. And perhaps that is why the question of before the Big Bang feels so compelling. It is not merely curiosity about history. It is a reflection of consciousness, trying to locate itself within a larger story. We want to know where we came from because we want to know what we are. But here is the quiet twist. It may be that the universe does not have a single, well-defined origin story waiting to be uncovered. It may be that the story is not finished, that reality is still becoming, still exploring its own possibilities. In such a universe, meaning does not flow from a beginning. It flows from participation. Our lives, our thoughts, our questions are not external to the cosmos. They are events within it. When we wonder about the beginning of time, that wonder is itself a physical process, encoded in neural activity, governed by the same laws that shaped galaxies and stars, the universe asking about itself through us. And there is something deeply moving about that image, not because it flatters us, but because it situates us. We are not spectators watching a cosmic drama from the outside. We are characters within it. Brief, fragile, but real. This reframes the anxiety that often surrounds unanswered questions. If we never know what existed before the Big Bang, that does not mean our inquiry has failed. It means that the universe has depths beyond our reach, at least for now. And perhaps that is as it should be. Mystery is not the enemy of meaning. It is its source. A universe that was completely transparent, fully explained, would leave no room for wonder, no space for curiosity, no reason to ask anything at all. The fact that there are horizons we cannot cross gives our questions weight. It gives science direction. It gives philosophy relevance. It gives art, music, and storytelling their power. As we look ahead, the future of human understanding remains open. New theories may emerge. New observations may push back the veil, or they may reveal that the veil has no edge, only layers. Either way, the journey continues. And so, rather than seeking a final answer to what was before the Big Bang, we might choose a different stance. We might choose to listen, to explore, to remain curious without demanding closure. Because the universe has already given us something extraordinary. It has given us the ability to ask, and perhaps that is enough, for now, as our thoughts continue to drift onward, not toward an ending, but toward the next question, quietly forming in the mind, waiting to be asked. And so, as this long journey gently circles back on itself, we find ourselves standing somewhere familiar, yet subtly changed. We began with a simple question, one that felt almost childlike in its innocence. What was there before the Big Bang? And along the way, that question led us outward across unimaginable scales, and inward toward the deepest limits of thought itself. We have wandered through many possible landscapes. We have seen the Big Bang not as a fiery explosion in empty space, but as the stretching of space itself. We have learned that time may not be a background river flowing forever, but a dimension that emerges, fragile and contingent. We have imagined universes without beginnings, cycling endlessly, collapsing and rebounding, or expanding forever. We have stepped into the strange richness of the quantum vacuum, where nothing is never truly empty, and where entire universes might flicker into being as naturally as particles appear and vanish. We have followed the logic of eternal inflation, where our universe becomes one bubble among many, and the word universe loses its singular meaning. We have entertained the possibility that reality itself may be layered, simulated, or fundamentally informational, with space-time and matter emerging from deeper patterns. And finally, we have confronted the quiet honesty of science, acknowledging where equations fall silent, where observation cannot reach, and where the universe offers no clear answer. Through all of this, one truth has slowly come into focus. There is no single, final, authoritative answer to the question of what existed before the Big Bang. Not yet. And perhaps not ever. But that absence of a final answer is not a failure. It is, in a sense, the most important conclusion of all. Because what science has revealed again and again is that the beauty of understanding does not lie in certainty alone. It lies in the process of questioning, in the willingness to revise our ideas, in the courage to admit ignorance, in the patience to sit with mystery without rushing to close it. When we ask what was before the Big Bang, we are not merely probing the early universe. We are probing the limits of explanation. We are asking whether reality itself must conform to the way human minds prefer stories to be told, with beginnings, middles, and ends, with causes neatly preceding effects, with time flowing cleanly from past to future, and the universe, gently but firmly, seems to be telling us that it does not owe us that structure. The Big Bang may not be a beginning in the way we instinctively imagine. It may be a boundary, a transition, a phase change, or simply the earliest chapter we can currently read. Before it may lie other chapters, written in a language we have not yet learned, or it may lie something altogether different, something that does not fit into chapters at all. What we do know is this: the universe is not simple, it is subtle, it is layered, it is generous in its mysteries, and perhaps that generosity is what has allowed it to give rise to us, to minds capable of reflection, to beings who look up at the night sky and wonder not just how the universe works, but why it exists at all. That, I suppose, is the quiet miracle at the heart of this story. Out of whatever existed or did not exist before the Big Bang, there emerged a universe capable of producing stars, planets, chemistry, life, and eventually consciousness. And that consciousness now turns back on the universe, asking about its origin. The universe questioning itself through us. This reframes the entire problem. The question of what was before the Big Bang may not be one the universe is required to answer. But the fact that the question can be asked at all is already an answer of sorts. It tells us that reality is structured in a way that allows understanding to arise, even if that understanding is always incomplete. And here, perhaps, lies the deepest lesson. The universe is not a finished book waiting to be read. It is an ongoing process, and we are part of that process. Our theories are not final truths. They are approximations, sketches, maps drawn by minds embedded within the territory they are trying to chart. This does not make them meaningless. It makes them precious. Every idea we have explored, from cyclic universes to informational reality, is a testament to human curiosity, to our refusal to accept the visible surface as the whole story, to our willingness to imagine beyond the horizon, even knowing that the horizon may always recede. There is a quiet humility in this, and humility, far from diminishing us, connects us more deeply to the cosmos. When we let go of the need for absolute certainty something else becomes possible. Wonder. A slower, more contemplative relationship with reality. One that does not demand that the universe explain itself on our terms, but invites us to listen, to observe, and to participate. Perhaps the universe does not begin. Perhaps it does not end. Perhaps it simply changes. And perhaps our lives, brief as they are small but meaningful threads in that ongoing transformation. In that sense, the question of what was before the Big Bang is not separate from the question of what comes next. Not just cosmically, but humanly. What kind of questions will we ask in the future? What kinds of theories will we build? What kinds of meanings will we draw from a universe that may never offer final answers? The future of physics may reveal deeper layers, or it may teach us new ways of living with uncertainty. The future of philosophy may help us articulate questions we have not yet learned how to ask. And the future of humanity will unfold within this vast, mysterious context, shaped not only by what we know, but by how we respond to what we do not know. And perhaps that is where this journey truly leads, not to an ending, but to an attitude of curiosity without arrogance, of exploration without expectation of closure, of reverence for a universe that is older, larger, and stranger than we can fully comprehend. We began by asking, what was there before everything? We end by realizing that the universe may not be something that can be reduced to a single origin story. It may be a conversation that has been unfolding far longer than we can imagine, and will continue long after we are gone. And in that conversation, our questions matter, not because they must be answered, but because they reflect the universe becoming aware of itself. So as our thoughts drift onward, beyond beginnings and endings, beyond big bangs and theories, we are left not with certainty, but with something quieter and perhaps more enduring, a sense of belonging within mystery. And that, I suppose, is a beautiful place to rest, as the next question slowly, inevitably, begins to form.